So in chapter 5, section 1, we've been talking about these identities, right? So we spent yesterday kind of discussing and deriving these identities that we've kind of collected all together on this identity sheet. This will be your friend. You'll consult this a lot. You may want your own physical hard copy, so you don't have to keep flipping your pages back and forth in OneNote or whatever, but let's look at some examples of the kinds of things you're going to be asked to do in your homework. So let's say we're asked to use identities to find the value of sine if tangent theta equals 3 and cosine theta is negative. So what I'm going to do is I want to look for a identity involving tangent specifically. Now, the fact that I'm given whether something is positive or negative kind of gives me the hint that I'm probably going to want to use one of the Pythagorean identities, because the positive or negativeness is going to be used to determine whether a square root needs to be a positive or a negative when I have to square root something. So I'm going to go ahead and use that third Pythagorean identity that involves tangent, because I know the value for tangent. Everybody's okay with that reasoning? Now, since tangent is 3, I can just plug that in. So I have 3 squared plus 1 equals secant squared. So 3 squared plus 1 is 10. And then to get the secant by itself, I square root both sides to get plus or minus 10. So far, so good? I noticed that on my identities, that secant is related to cosine, that they're reciprocals. And I know something about cosine, so that's what I'm going to do next. Since cosine is the reciprocal, or secant is the reciprocal of cosine, or cosine is the reciprocal of secant, think about it either way is fine. I can say that, right? And since cosine is negative, I know I can drop the plus from the plus or minus, and that this has to just strictly be negative 1 over the square root of 10. So far, so good? So now I know a value for cosine, and I know a value for tangent. So I'm going to go back to my identity sheet and see if there's something that involves sine and cosine and tangent. Specifically, I see this identity right here, the first quotient identity, that tangent is equal to sine over cosine. That involves the 3 trig functions that I'm interested in. if I multiply both sides by cosine theta, I get that sine is equal to tangent times cosine. And then I know cosine is negative 1 over the square root of 10, and tangent is 3. So when I multiply this stuff together and I rationalize the denominator, I get that guy. Again, you could have rationalized the denominator on that cosine at any point. I just usually wait to the end to do that because it's less writing to not have all the extra stuff until the very end. But you can do it whenever you feel like it. You know, if you're one of those people that, like, if I don't do it when I see it, I'm going to forget. Just do it when you see it, man. It's okay. Questions about that one?
I have a question.
Yeah.
Which page of chapter 5 was story from?
2. It's the bottom of page 2. Is the example that I'm referring to. I think the work for it rolls over onto page 3, but okay, no problem. Okay. So that's one kind of problem you're going to be asked to do in the homework. The majority, though, of the things you'll be asked to do are going to be these simplify the expression kind of problems. So when we're asked to do these simplify the expression problems, what we want to do is end up with like the simplest version of this that we can. Ideally, that means we're going to get it down to like a single number or a single trig function, or, you know, some of them that are messier maybe not go down that far or that much, but we're going to combine it the best we can. Okay with that idea? The tools we have are going to be basic algebra things. So like factoring or foiling or finding a common denominator, you know, to like add fractions or whatever. It's going to be basic algebra things. And then our identities are going to be the two sets of tools we have to kind of do these simplifications. Okay with that? Now, typically what I do is I think it's usually easiest to start by looking for algebraic things, take care of that stuff, and then move to the identity things. That's not always got to be the case, but that's typically kind of what I start with. So if I look at this example, sine cubed x plus sine x times cosine squared x, do you see any algebraic thing that we might want to do here? Or that we can do here even? Well, we can't add the signs together because of that. One, they have different exponents. And two, the other sign has the cosine squared attached to it. But the fact you have two terms that both contain a sine should be a hint as to what we can do algebraically. Yeah, we can factor a sine x out of each of these, right? That's what I would do first. So when I factor a sine out of sine cubed, I get sine squared. And when I factor sine out of sine times cosine squared, I'm left with just cosine squared. So if everybody see kind of what we did there with the factoring, just like a greatest common factor is all we pulled off. Now I don't notice any algebraic thing left I could do here. I mean, all I could really do is just distribute the sine back through, but that's just right back to where we started. Why would I do that? So I'm going to go and look for an identity. Take a look at our identity sheet and see if anything sticks out. There is one that should be like screaming at you. Yeah, so in it's the first Pythagorean identity. It says sine squared plus cosine squared equals 1. If I look at our problem, we have a sine squared plus cosine squared. So I can use that first identity to replace that part with a 1. And then sine times 1 is just sine. And that's as far as you can go because we're down to a single thing, right? What do you guys think? Let's do some more examples. So let's say I have secant x minus 1 times secant x plus 1 all over sine squared x. Do you guys see an algebraic thing that you might want to do here first? Well, it's already in factored form, right? Do you mean FOIL?
Yes.
That's what I would do, absolutely. And why foiling seems appealing to me is that I have a difference of 2 squares here, right? Like I have an a minus b times an a plus b. Everybody's okay with that? So when I FOIL this out, I get this. Everybody so far so good? Now I look at this, I don't see any other obvious algebraic things to do. You guys agree with that? Okay, I mean I could factor the numerator, but that's just going to put me right back to where I started, right? Why would I do that? So let's go look at identities. So there's one identity amongst this here that we're looking at that I think looks really appealing to me. It's maybe not super easy to see, but after I point it out, hopefully you see it. I'll give you a hint. Because everything has a squared on it, where are we going to probably be looking? Probably the Pythagoreans. Amongst the numerator and denominator, both have something squared in it. Which one would be the more likely place to want to be looking? I would say the numerator because I have the minus 1 to go along with it. All these Pythagoreans have a 1 in them as well that's being added or subtracted or whatever. So I think the obvious candidate is P3. Right? We have a secant squared in our numerator that I can replace with tangent squared plus 1. Okay with that idea? And let's look at the good things that happen because of that. So now the plus 1 and minus 1 can combine together to give us 0. And we're left with just tangent squared over sine squared. That's an improvement, right? We got rid of all the addition and subtraction going on. We're down to a single fraction. That's an improvement. Is there more we can still do? Well, sure. So what I would typically do in this kind of situation is I'm going to think about these as the product of two fractions. So I'm going to think about it as like tan squared times 1 over sine. And the reason that I'm going to do that is because I know I can rewrite tangent in terms of sines and cosines. If I look at my identity sheet, the first quotient identity says tangent is equal to sine over cosine. So tangent squared is going to equal sine squared over cosine squared, right? And that's what I'm going to use. And I'm interested in that one because when I do that, I'm going to be able to cancel the sine squareds. Everybody's okay with that? Now you'll see that the reason that I separated the tangent squared and the sine squared into two fractions like that was just so I didn't have fractions on top of fractions and have things get kind of confusing, which is a nice trick to be able to use. Everybody okay with that idea? It is cosine. Cosine squared. Yeah, so now we have 1 over cosine squared. And that I should recognize immediately. What is that the same as? Secant squared. Yeah, excellent. And we've got it down to a single thing, so that's as good as we can do. Ava? Absolutely. No problem. Let's do another. Well, let's see is what we're on. Okay, so let's take a look at this one. Here we have cosine x over 1 minus sine x minus sine x over cosine x. First thing we do is typically look to see if there's any algebraic stuff we might want to do. Do you see any algebraic thing to do on this one? I see something that I would want to do.
Would you cross out the sine x's?
So no, for a couple of reasons. One, in the denominator you have 1 minus sine x, so you can't cross off part of an addition or subtraction problem. And then 2, the symbol in between the two fractions isn't multiplication, it's subtraction, so you definitely can't cancel numerators and denominators across addition or subtraction symbols. So that we can't do, but there is something else that we might want to do when we have two fractions and subtraction going on between them. Distribute. Mia, let's make a common denominator, right? If we want to add or subtract fractions, the first thing we'd want to do is make a common denominator. Does that feel okay with you guys? So what would the common denominator be between these two fractions? Should be pretty easy. What do you guys think? What would that common denominator be? Wouldn't it just be 1 minus sine x times cosine x? Right? Just the product of the two denominators would be the common denominator in this case. No? Sure it is. Sure it is. So the first fraction I'm going to multiply by cosine over cosine. And the second fraction by 1 minus sine x over 1 minus sine x. Everybody so far so good? Okay. Actually, I'm not going to distribute in the denominators. Why wouldn't I want to distribute in the denominators? Nobody with an idea? If you think back to when we talked about rational expressions last year, when we reduced those rational expressions, the numerator and denominator both had to be in a factored form to do any reducing, right? That's the reason why I'm not going to bother factoring the denominator or distributing out the denominator, because if I want to reduce later on, I would just have to factor it back anyway. So let's just leave it factored. You know what I mean? Everybody's okay with what I did here? Let's distribute that negative through. That seems like a pretty obvious thing. To kind of complete the subtracting of fractions there. Does anybody else see an algebraic thing that they might want to do here? I don't, right? Can't reduce anything the way it's written because you have an addition and subtraction problem on top. There's no factoring I can do on that addition or subtraction problem because there's no like term amongst anything. Nothing's really quadratic. It's nothing I can really do with that. So what should I do then? look for an identity. Okay. Where would I probably want to be hunting for my identity? Personally, I'd be wanting to look at the numerator because I want to get that sorted out. Since the denominator is already in a factored form, I'm probably not going to want to mess with that a whole lot. But the numerator, maybe there's something good I can do up there. Does anybody see anything that we could do in the numerator? Ella? Yeah, very good. So again, that's the first Pythagorean. Sine squared plus cosine squared is 1. So I can just take those and replace them with a 1. Aha! Who sees something good now? Mackenzie. Yeah. The other one. Yeah. Everybody happy with how we finished that one out? Is the pace okay here, guys, as we're going through these? I'm trying to be really slow and deliberate and kind of talk through internally what's happening in my head. If that's not helpful or you need more, stop me and say something. It's okay to do that. Oops. We're on D now. Yes, sir. Absolutely. All right, let's look at this one. We have sine x times cosecant of negative x. Is there an algebraic thing I can do here? No, right? We just have two things multiplied together. They're not like things, so there's, what can I do with this? Nothing, right? The way it's written. So I'm going to go look at my identities. There should be something that screams out at you right away when looking at this that we would want to sort with or sort out first. Does anybody have any idea what that might be? I'll give you a hint. Are the variable parts the same on this? Am I going to be able to multiply them together while the variable parts are different? First identity I'd want to use is one where I can get the variable parts to both be the same. So looking at my identities, I'd want to be using this odd-even identity 4. Allows me to take cosecant negative x and rewrite that as negative cosecant x. Feel okay with that, everybody? The odd even number 4. And then just let's get rid of the parenthesis, or the bracket, I guess is what I wrote in this case, because just felt like there's going to be a lot of parentheses there, so I just chose to use a bracket instead. Right? I multiply a positive thing and a negative thing together, just becomes a negative thing, right? So I'm just going to move the negative sign out front. It's kind of the more standard location for it. Then it helps it not look like a subtraction problem and have me get confused a minute later. Everybody feel good there? Okay. What do you think we should do next? Both the variable parts are the same now, right? They're both just regular old x's. That's great. I would go look at identities again. Ella, do you have an idea? Yeah. Yeah, let's just put it this way. I like that plan. That's what we did here and there. So what can I do there? Now they got it written like this. Cancel the signs, right? So what's left? -1. Definitely can't beat that, right? You get down to a single number. Ooh, doggy. All right, we got one more example to do. I'm going to use a bracket here instead of a parenthesis. You guys know brackets and parentheses are really the same thing in a problem like this, right? I'm just using brackets because if there's a lot of parentheses, sometimes it just gets hard to keep track of everything. It's mostly just for like neatness sake on my part. All right. So typically we like to start by looking for algebraic things that we could do. What algebraic thing could we do here? Is there anything? Ella? So that's using an identity, which is fine, but I'm not sure that's what I would do first here. Well, the obvious algebraic thing would be to like just distribute things through, right? Because you have a multiplication problem outside of a parenthesis. Everybody see that? I'm probably not going to do that first, though. Mostly just because I don't want to write down that, or because I also observe that the variable parts are different, right? So I multiply that through, then I'm going to have two things where the variable parts are different instead of just one. This is a case where I would probably deal with that cosine of pi over 2 minus y part first, and then I'll do the distributing. Just because it makes a little bit more of a mess to do the distributing first. Do you guys get that? So if I go and I look at my identities, I'm going to look for something that'll help me sort that piece out. So if I look at my cofunctions, I know that cosine of pi over 2 minus theta is just sine. You guys see that? So that's what I'm going to do first. And then I'll distribute the sine through. Does that feel okay? Everybody so far so good? So the only algebraic thing I might be able to do would be to pull out that greatest common factor of sine. But in doing that, I'm just back to where I started. So like, why would I do that? So I think it's identity time here. And Ella had, before had suggested rewriting cotangent as 1 over tangent. I would probably use the quotient versions here. And let me explain why I would do that rather than writing it as 1 over tangent. It's because now I have it multiplied by sine in each case. Using the quotient versions for tangent and cotangent gets it in terms of sines and cosines, so maybe there's some canceling or combining that can happen there. You'd still be okay to do what you were suggesting, Ella, but I think it's going to end up making a little bit more work for us later on. But I like where your guys' heads have been and making suggestions of like, hey, this is what I would think to do. Even if they're maybe not the best choice, I think is really important because it gives me an opportunity to kind of talk about like, hey, okay, is there anything wrong with what you suggested? No, perfectly reasonable thing to do. But I wouldn't do that because in my experience, I've seen that like this, and this, why something might be a better choice. And that helps you, right? That's how you're going to learn how to do this is you don't have any intuition yet. We need to develop that. What's the best way to develop some intuition? Try things out and see what works and see what doesn't. If I can make that process a little less painful by like not letting you try bad things right away. So we build some intuition about like what are the effective things to do first. That's just going to make life a little bit easier. So the more you can kind of participate, even if it's in your own head with like, hey, what would I think to do next? Like when we pause, like really try to think about that, and see if what you were thinking. And if I decide that we want to do something different than what you were thinking, you can certainly ask like, hey, is there really any difference between doing this and doing that? Or like, why didn't you want to do this? Those are, I think, really important questions that would need to be answered. And I'll do my best to kind of address those throughout this chapter because you guys haven't ever done this before. Well, most of us haven't ever done this before. And there's, how else are you going to develop any intuition unless you're trying and getting some feedback, right? Okay. So you see that we replaced the cotangent with cosine over sine and the tangent with sine over cosine. Hopefully you notice that the signs can cancel in the first pair of fractions. And then the signs can combine in the second pair of fractions. So we still have these two fractions now. What would you want to do here? Make a common denominator. Yeah, what would that common denominator be? Cosine y. So I'll multiply the first fraction by cosine over cosine. The second fraction I don't have to do diddly poop to because it's already got a denominator of cosine. So that's going to give me cosine squared y plus sine squared y. Oh boy. All over cosine y. What do you guys see there? It should be flashing at us pretty brightly. Yeah, that first Pythagorean. Sine squared plus cosine squared is 1. Yes. And then 1 over cosine is just secant. Are all of them just equal to secant? Like that's happened a bunch of times here on these examples. What do you guys think? No, that's a silly statement. They're not all equal to secant. They just happened to pick, Mr. Kulik picked some weird examples where they all kind of simplified down to secant. Oh, that's funny though. If you can't laugh about weird things happening, I don't know what's wrong with you. Okay. We're going to stop here. At this point, you guys should be able to handle 1 through 14. Now, this 1 through 14 isn't due this week's homework set. It'll be due into the next week's homework set, which you can see I've already added to the board there. Any questions about anything else here before we stop for today?